Last we talked about the first of two searches for trees, the breadth first search. And we got all the way through kind of talking about the pros and cons of breadth first search. So as a recap, breadth first search is using level order traversal. It's going through the tree at level 0, which is just the root, and then level 1, which is the children of the root, and level 2, which is the children of the root, etc., all the way down the tree. So the pros of this were that if there is a solution, it will return to you the shallowest solution in the tree. You're searching for a value. If we allow duplicates in the tree, it will return the one that is closest to the root. The con of this is that you need a ton of memory as you build a really large tree structure. You're keeping the entire next row in memory because it's all in the queue. And each row can be up to twice as large as the last row. So if you have a tree of depth 40, you're going to have 2 to the 40th number of nodes in your queue by the time you're done with it, which is ridiculous, and nobody has any. That's outside the scope of what can be stored in RAM outside of a supercomputer in today's day and age, which, I mean, many things are going to have depth 40 out there. If you're actually thinking about big data and how much data is actually being collected out there, maybe you want to store that in some kind of tree structure. So a breadth first search might not be a viable search for data that is that big. So the complexity of this, think about how much memory needs to be stored and how much time it's going to take to do that. So think about the number of nodes that are stored in the entire tree structure. The breadth first search is going to take time proportional to the number of nodes. You'd expect to search through about half the nodes, since it's kind of a sequential search, kind of like searching through an array. Since it's not necessarily a binary search tree. If it were a binary search tree and we were using our find algorithm from the tree, then it would be logarithmic because we would be able to remove half the tree as we go. But if we are not able to make an intelligent structure with an intelligent search in it like that, then we actually have to manually go through every single node and just check, are you it, are you it, are you it? So you just need some way to make sure that we get the entire tree structure. The memory requirement becomes exponential based on the level of the tree. So it's not exponential based on the number of nodes in the tree, but with the number of levels in the tree, you will end up needing to store 2 to the level number of nodes on the horizon of the next level that you're going to be looking at as you go. So that's a huge downside to it.
So the memory storage is going to be exponential to the number of nodes?
The number of levels in the tree. So the height of the tree.
And then so is the runtime complexity going to be linear then, or?
It's linear with respect to the number of nodes in the entire tree structure. Yeah. So the other major search that we can talk about is the depth first search. So depth first search uses in order traversal instead of level order traversal, which is useful in a binary search tree. So this is going to search them. If you had a binary search tree, you would output it in order by the in order traversal, so from lowest to highest. But what that means in terms of how it actually searches through the tree is it's going to go left, 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 all the way down. And the very first node that it's going to search and look for is quite possibly one of the deepest nodes in the entire structure. It's not going to start with the root. It's going to start with whatever is left, left. The root's lefts, 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 lefts until it doesn't have one. Then it's going to explore that, go back, go right, and do it in order. So left node right order. So thinking about this versus breadth first search. What are the pros of depth first search compared to breadth first search? What does depth first search do better than breadth first search?
Probably has to search less things, less items.
If it's probably going to be still sequential in that we don't know if it's going to be the very last element on the rightmost part of the tree, in which case depth first search would output it last, so I would still expect that we probably have to search through half the items.
So you're gonna use a queue, right? So that's.
Right. Yeah, it is certainly more memory efficient. So thinking about a tree, the tree's width grows exponentially compared to its depth. You have 2 to the depth number of nodes on that particular level. We have 1, then 2, then 4, then 8, then 16, and the depth is growing linearly. So the most nodes that we need to store in memory are actually the depth of the tree and not the width of the tree. The depth of the tree is going to be significantly smaller than the width of the lowest depth. Because we only need to care about how many levels have we visited, so we need to know where to go back to explore the node right version of the in order traversal, if that makes sense. Let me actually draw that out, make the visual with help here. What color is gonna happen once I'm thinking. So I'm gonna draw a fairly deep tree here, hopefully. I should probably, if I'm gonna do that, make this very wide. Maybe this is enough to start visualizing just how much the width of something explodes more than the depth. But this just gets more and more pronounced the deeper you go. I can start drawing the. Just even the connectors give you an idea of the next level and how many nodes are gonna be on the next level when you're just adding 1 to the depth. So we have depth 0, 1, 2, 3, 4, and already at 4, we have a lot of nodes. We have 16 nodes on that level, there'll be 32 nodes on the next level, there'll be 64 nodes on the next level. This explodes exponentially. You can imagine needing a queue to store all of these elements, whereas depth first search, you're just gonna go, it needs to store this as it goes left. It needs to store this as it goes left. It needs to store this as it goes left. It needs to store this as it goes left. So way fewer items in memory than we had with that. The downside is that this is usually done recursively, and if it's done recursively, then it's stored in the stack portion, like we have different stack frames for each of these. So we end up with a stack overflow, but only if we get to about depth 40, which we already said we don't have enough memory in our machines to store all of the nodes at depth 40 anyway. So because of this, if you have a memory constraint or a large structure, depth first search is going to be significantly better at searching it. It's not going to be faster necessarily, but it will take less memory because you need to store fewer elements as you do this. If you're going to store the next node down here, you can get rid of this node that we're storing here as we go backwards, explore this node and go right. At no point are we going to be storing more nodes to backtrack than the depth of the tree. Does that make sense? Questions about that? So the big pro we have is that memory is proportional to the depth of the tree rather than the width of the tree. And the width is going to be growing so much faster than the depth is for any large tree structure. What about cons? What are some of the cons of depth first search compared to breadth first search? Yeah.
When the query is found, it's not really only gonna be the shallowest.
Yeah, exactly. How would we guarantee that that it would be the shallowest node. We'd have to do a lot more searching to actually be sure that we found the shallowest node. You'd have to have a really intelligent algorithm that says, maybe I found it at depth 6. Search depth 5 and less of the tree all the way until you're done with that. If you don't find it again, then great. If you do find it again at depth 4, restart searching only up to depth 4. And that might take significantly longer. You can actually, as you explore in algorithms, you will find that there are other algorithms that work. Like you can do a depth first search up to a particular horizon and then just expand the horizon. That kind of combines breadth first search and depth first search. We call this iterative deepening. And this allows us to get the memory requirements, the memory of a depth first search. And we know that when we find a solution, it is the shallowest solution. And it doesn't actually have a worse order than breadth first search or depth first search, but it does take longer. But you get that extra requirement. So the big con here is that there's no guarantee, exactly as Connor said, when the query is found, that we found the shallowest solution, the shallowest copy of that query. We still have the same complexity that we did for the breadth first search, except that the memory requirement is now less. The memory requirement is now, instead of being exponential with respect to the depth, it is linear with respect to the depth. Which is a significant benefit. But depending on the use case of your traversal, it may not be the best thing, because we may be looking for the shallowest solution, in which case we would rather have a breadth first search and actually spend the memory that we need to ensure that the solution that we get is the shallowest solution. So that's why we study both of these, is that they are both relevant and valuable for different searching requirements. But there are some intelligent searches, especially once we start talking about graphs. You can get some very intelligent searches. If you're curious, you can go look up A star. A star is a pathfinding algorithm that is incredibly useful in games, game design, anything that involves traversing from one element to another. You know where the goal is, and you need to be able to go around obstacles. It will find the shortest way in the fastest time to get to that goal, regardless of what is in the way. Kind of a scary algorithm when you think about actually using it for artificial intelligence. You cannot outrun being chased by a star, because it will optimally chase you. So that's all we have for trees. We're gonna hop into the next structure, which is something that we visualize using a tree, even if we don't use a tree structure underneath the hood to store it. And that is heaps. Once we finish with heaps, we're gonna go back to sets and maps. Now that we've seen both hash tables and trees, those are the two structures that we use to, underneath the hood, represent a map set. And that's also used as part of a dictionary or map. So we're gonna study all of those because for some reason, historically, this class does not touch on sets and maps, and they're among the most widely used data structures out there. So I don't understand why they aren't covered and why students in 400 level classes don't know they exist. So of course, trees are useful for more than just binary searches and binary search trees. They are used in a lot of other places. We visualize this structure called a heap as a tree, even though we underneath the hood store it for that. There's another very efficient sort that we're going to cover called heap sort. I'll actually implement that in class. The concept of a priority queue is also used as a heap underneath the hood. So a priority queue is just a queue where you can assign a bunch of different tasks an associated priority. So maybe high priority, middle priority, low priority. And then you want to say, get me the next high priority task. And whenever you insert into the heap, you insert in an associated priority, and it will reorder itself such that when you remove from it, you remove the highest priority items first. So that uses a heap underneath the hood, so it's very useful for things like scheduling. Very useful for a lot of tasks that you would want to write a program for. Where the underlying structure has a priority. And you don't want to resort an array every time you insert. So heaps come in two forms, max heaps and min heaps. And it's just a matter of when you remove from the heap, do you get the largest item or the smallest item? So it's kind of like a stack in that you don't have access to every single element in the heap. It's more like a stack or a queue. With a stack, you only have access to the last thing that you put in. With a queue, you only have access to the first thing you put in. With a heap, you have access to only the largest element or only the smallest element, regardless of the order that they were inserted. So we're going to keep some kind of balance that allows us to easily access the largest element or the smallest element. So we're going to tackle this from a max heap perspective. So we're always looking for the largest element. So you can think of it as a tree structure with these restrictions. These are very important restrictions because they define what a heap is. So in a tree structure, every parent must be greater than all of its children. Every level of the tree, except for the very last level, must be full. And by full, we mean that every node has two children. So it's a binary tree structure. Every node is going to have two children unless we're at the last level or the level before the last. Meaning that as many nodes as fit in that level are in that level. So if the last level is not full, the last thing is all nodes are as far left in that level as possible. So let's draw a few and determine whether they are legal heaps or not legal heaps. So let's just first, without even looking at numbers, let's look at the structure of the heap. So we'll start with something like this. Is this a heap?
Yes.
Yes. Is this a heap?
No.
No. In order for this to be a heap with 4 nodes, where does this node need to be? Yes. So this, everything except for the last is now full. We can't add another node at this level. So this has to be as far left as possible. This is now a legal heap. If we're adding again, we're going to add here. If we're adding again, we will add here. If we're adding again, we will add here. Does that make sense? Every level has to be full except for the last one. The last one's nodes have to be as far left as possible. So no internal node is going to have one child, unless that child is as far left as possible in the last level. That's the only time a node would have one child. So almost everything has 2 children, unless it's a leaf that has no children, or it is in the level before the last one, and it's pointing to a single node that's as left as possible. And then just for every level of this tree, we need to make sure that the value that's in that node is greater than all of its children. So is this a legal heap? Yes, it is. There's nothing that says about level order, because this is deeper in the tree and it's larger than something that's shallow in the tree, that is allowed. All we care about is that for each node, we look at its 2 children, it's larger than its 2 children. 20 is larger than 19 and 16, 19 is larger than 18 and 17, 16 is larger than 15 and 14. Legal heap. So those are the most commonly confused elements of the heap. They'll look at this and say, but 18 is bigger than 16. That is allowed. Questions on heap rules? Yeah.
So are you ordering that in that certain way to follow those lists, or how does it know?
Yeah.
Okay.
Yeah, it has to follow all 3 of these rules. If any one of these rules is broken, then we don't have a heap. You just have a binary tree. In order for it to be a heap, these rules need to be followed in order to get the runtime guarantees that we will ask for from a heap, as well as the benefits that we'll ask for from a heap.
And it only cares if the parents greater than both of the children.
Yep. And we will see why we can relax to be completely like that. We don't need any other structure to this in order to be able to insert to this structure in logarithmic time. Remove from the structure in logarithmic time. And then be able to acquire the maximum value in constant time. So we can get that, and then to reshuffle the heap is logarithmic time. Yeah,
I think you said we're just doing max heap in the class, but with mid heap.
it's exactly the opposite.
It would be the minimum.
Yeah, everything else is still the same with this, it's that every parent is now less than all of its children. Other questions? Does this make sense? All right, we're gonna skip this because we did this on the board. So, where is the largest element? At the root. Is it always at the root?
Is it, when you have your kids, like, they bigger, right?
If it's a mini. But if it's a max heap, then the largest node is always the root. So we always know where the largest is. If the goal is to get the largest element, we know it's at the root. There's no traversal of this tree that is necessary in order to get that. So imagine now, we've drawn this as a tree, and in fact, I would highly recommend, if you are using a heap or a heap-based structure, think of it as a tree. But underneath the hood, we're actually going to use an array list. Why do we, can anyone visualize why we might use this as an array? Rather than as a tree structure? First of all, how would you store the nodes of a heap in an array list? Well, if you call sort, you're gonna go through an n log n process to sort. And with a heap, we want to be able to do that in logarithmic time, not n times logarithmic time. It's a good idea. The key comes down to the fact that we're gonna store in the array in level order. So what that means is that I have a heap. Let's say I have a fairly small heap like this. Give me some values that adhere to a legal heap. What is the root?
The max heap.
Max heap. 35. What's 35's left child?
34.
What's 35's right child? 8. Love it. What's 34's left child?
7.
What is 34's right child? What is 8's left child?
6.
I hear a 6 and a -3. Both of those will work just fine. So if we're going to make an array that is this structure, we're going to basically, there are 7 elements. We're going to have 35 stored here, 34 stored here, 8 stored here, 7 stored here, 17 stored here, 6 stored here, and -3 stored here. Index 0, 1, 2, 3, 4, 5, and 6. So we're storing this in level order. So this is equivalent to this, is what I'm going to argue. In terms of getting the same guarantees that we want out of a heap. This represents that concept. So now, given a node index, where is the parent of that in this structure? So let's say I want to find the parent of -3. Where is the parent of -3 in this structure?
One, previous time.
It's an index 2. Interesting. Where is 6's parent? Index 2. Where is 17's parent? 1. Where is 7's parent? 1. Where is 8's parent? 0. Where is 1's parent? 0. All right, find a mathematical expression that gives me an index. Where is its parent? And this will work in general for an array of any size, as long as it's stored as a heap. Where is the parent?
Zero or?
It's always, so 6 maps to 2. If we wanted to come up with a table for this, maybe that's a good way to do this. We have the index and the parent of the index. So when we have 0, this is irrelevant. When we have 1, it is 0. When we have 2, it is 0. When we have 3, it is 1. When we have 4, it is 1. When we have 5, it is 2. When we have 6, it is 2. What expression, what mathematical expression maps I to P of I? Close. Since we're in computer science, we're free to use integer division. That might help. Close. As this grows, where would index 7 map? 3. Where would 8 map? 9 map? 4. Yep. What's the expression? What computer scientists run from that? Subtract 1 from I divided by 2. This is just integer division, so if there's a remainder, you lop it off. 6 minus 1 is 5, divided by 2 is 2.5. Toss off the 0.5, you get 2. 5 minus 1 is 4. 4 divided by 2 is 2. 4 minus 1 is 3. 3 divided by 2. Lop off the remainder is 1. And this will scale as well. So the parent of I is an index, I minus 1 over 2. Next one, given a node's index, where is its left child? left child of I. But as a general expression, that would get us the left child of I.
Two plus one.
That's exactly right. How about the right child of I?
I don't think the left child, so it would be like times 3 plus 1.
So if I is the root, and we want to find the index of this, 35 is sort of index 0, 2 times 0 is 0, plus 1 is 1, which is the index of 34 in the array. If we wanted to find the left child of 34, 34 is sorted index 1, you take 2 times 1, which is 2, plus 1, which is 3, and what's sorted index 3 is the left child of that number. And in general, that will work for any node. You take 2 times the index in the array where it is, add 1 to it, and you will find its left child in this tree structure. Its position in the array.
The 2 times that plus 2.
Yeah, exactly right. The right child is always 1 index greater than the left child. So you just add 1 to the expression for the left child to get the right child. So these are the 3 relevant expressions to map how to get from one node to any node that it connects. For any particular node in the tree structure, you can get to the parent, you can get to the left child, or you can get to the right child. That's all we care about. And now we have expressions given the index of where this is stored to access the parent, left child, and right child, which is all we care about. Questions on how we derived any of these, questions on what any of it means, how we can show kind of an equivalence now between a tree structure and an array where we have stored the node data in level order in an array. Right. Let's talk about the actual insertion process. So how do we add things to this existing heap? So we start with, where is the next open position? So think about if the last row is not full, then find the leftmost null child, basically, the leftmost next position. We have. So let's say this is currently our heap. The next open position in the heap is right here. The leftmost place in the last that has a null child. So you would insert here. If the last row is full, you'll make a new row and insert it at the leftmost position in that row. So the next place to insert would be here. The next place to insert would be here. The next place to insert would be here. Of course, as we do this, we are probably violating some of the heap's rules. You can imagine that we had, until we did this, we had a legal heap. I will continue to use 35 as a root and 17 because we love 17 so much. We'll have 20 here, 3 here, and 9 here. All right, great. This is a legal heap. If we want to insert here, and we want to insert the number 60, we no longer have a heap that is legal. We agree? What can we do to efficiently turn this into a legal heap?
Why is that not legal?
60 is bigger than 17. So really 16, since it's the largest in the entire heap, should be the new root. But there is no way for us really to know that.
You can't, since it's stored in an array, can you just swap between 16? It's not
We
like-
could. Yeah, we're basically going to do exactly that. So we look at this node and we say, are you greater than parent? If so, swap. If we do this swap, are we guaranteed to still have a legal heap? If there's a value that happened to be, let's say we're inserting the 60 right here. And there was some value that was right here. What are all of the legal values that could be in this node such that we would have had a legal heap before we inserted the 60? Yeah, something that is less than 17. So if we swap the 17 and the 60, is this a legal heap?
Yeah.
Yes, it doesn't matter what this is, as long as we had a legal heap before we started. This is going to be bigger than that if this needs to swap with that. So that's the logic behind why this can happen. Let's just give this a value and say that this was 15. So now we swap the 60 and the 17. Is this a legal heap? Not yet. We take the current node and we query the parent and say, are you bigger than the parent? If it is, and we decide to swap, are we guaranteed to have a legal heap? Yes. We know the 35 is greater than this, and if this is greater than that, then this is also greater than that by the rule of triangulation, whatever it's actually called. So we're gonna swap the 35 here. This is still a legal substructure. We're gonna put the 60 here. Now do we have a legal heap? Yes. So this is how insertion works. Thinking about the complexity of insertion, we're gonna call this procedure either heapify up or up heapify. Those are the technical, believe it or not, this is actually what they're called. These are the technical terms when you leave computer scientists in charge of naming things. This is how you get voting with vote face and other fun things. Don't let the internet or computer scientists name things. Please take over and put some sanity back in this field. So this is the up heapify procedure. What is the complexity? What are the maximum number of swaps that we're going to be doing based on the tree structure? Yeah, it's based on the height of the tree. This is why we get logarithmic time insertion. Regardless of the number of items that are in the tree, the height of that tree is going to be based on the base 2 logarithm of the number of nodes that are in the tree. So if we're doing something based on the height of tree, it's based on the logarithm of the number of items that are stored in the tree. So we get logarithmic time insertion. So here's the actual procedure. We're going to insert it into the next open position. Compare the current node, the node you just inserted, with the parent. If the current node is greater than the parent, swap it. Look at the current node, is it greater than the parent? If it is, swap it. Look at the current node, is it greater than the parent? If so, swap it. Continue that process until that is false, or there is no parent because you're at the root. So we already answered this. Will this always produce a new legal heap? Yes, it will. The complexity is logarithmic with proportion to the number of nodes in the structure. Since we're making at most one swap per level of the tree. How do we feel about insertion? Does that process make sense? Feel like you could write the code for that, given a heap structure? We're gonna be doing that together eventually. Probably next class, since we only have a few minutes. But I want to at least take the next couple minutes and introduce the idea of deletion. I don't know if we'll get all the way through it, but we'll come back to it tomorrow if we don't. So removing from a heap or deleting from a heap. One nice thing about the max heap is that we only ever care about the largest value. This is why it's useful for something like a priority queue. Whatever has the highest priority is going to bubble its way toward the top of the heap via the insertion process. So whatever is at the root is something that is of the highest priority. Or if it's something that is sorted or needs to be sorted, then you have access to the largest element, you know, right where it is. So where is it? At the root. To delete the root, maybe we can generate this. What would the algorithm look like to delete the root? Try to keep this within logarithmic time as well. So have only one procedure to do or one thing to do for each level of the tree. Kinda, yeah. We need to make sure though that we end up with a heap that is a legal structure that has, if you delete the root and only move something or something up, you may end up with something that's not as far left as possible. So it's very close. It's actually very close to the right answer. Basically, the answer to this is that you're gonna swap the root with the last element in the heap. Then you can delete the root. And now we want to bubble the new element down the tree. Just like we up heapify with the insertion, we're going to down heapify with the, and this is the technical term for it again, we're gonna down heapify with the swapped element. So let's come up with a quick example. We have 2 minutes. I can at least try to visualize this. I decided to just go with a bunch of powers of 2. So now to remove the 35, we're going to swap the 35 and the last element in the heap, which is the 1. So we're going to swap. Then we're going to remove and return the 35. So that's gone. Now we need to down heapify the 1. How do we do this without breaking the heap's legality? Does it matter whether we swap it with the 17 or with the 4? One of these creates a legal heap, or at least a partially legal heap, and one of them we mess up.
Have to go left,
Yeah, we have to go left. Why?
because a legal heap will have.
Yeah, so the answer is to swap it with the largest child. It's not always the left, it's not always the right, it's whichever child is larger. So we need to do a comparison of the left child and the right child, say which of you is larger, and then swap this with the largest child. So we're going to swap the 17 and the 1. Now we can look at this level and say, are you larger than both of your children? No. So we need to swap it with the largest child. The largest child between 16 and 8 is 16. So we're going to swap there. And now we're down to a legal heap, and we did at most 1 operation per level to get there. So insert at the end, up heapify, delete, swap with the last element, delete the last element, down heapify. By comparing to the largest child. So down heapify is slightly harder than up heapify. If I say heapify one more time in this class, it's gonna start sounding funny. Questions on that? All right, we'll come back to it tomorrow and we'll start implementing a heap structure with an array list in code in class.